Hi everyone. In this video I'm going to be discussing some examples or illustrations of how we can compute the large sample confidence interval for two large samples. So we have some conditions that we need to have met in order for this approach to be valid. We require two random samples that are independent and drawn from two different populations. We require that both samples are sufficiently large, so larger than 30. And when those conditions obtain, we know that the sampling distributions of the difference of the sample means is approximately normal by the central limit theorem. And also for large samples, we know that the sample variances are going to be pretty good approximates of the population variances. So now under these conditions, we're able to build one of two confidence intervals according to whether or not we know the population variance or if we have to estimate the population variance with the sample variance. So now notice both of these confidence intervals are of the same form as any previous we've seen. So every confidence interval is just going to be centered on a sample statistic, and in this case the sample statistic is the difference of sample means, and then extending in the positive and negative direction to a bound that's created by the product of our critical value, whatever we've specified it as, and a standard error. Right, so we can test a series of hypotheses. If we're using a confidence interval, we're implicitly testing the first one, which is a two-sided test. And so we might test that there's no difference in means. That's probably going to be the most common. Alternatively, we could set, rather than 0 here, we could have any size difference in means that we're interested in testing against the alternative that the difference in means is not equal to whatever that value is. But for the sake of introduction, we'll just speak about this in terms of being 0. The other test we could have would be that, that one of the sample means is larger than the other. Right, so here's an illustration for the first and probably most common hypothesis test. So we want to test that there's no difference in sample means against the alternative that the population means differ. So we'll base our test on a comparison of the sample means that we've drawn from two samples from two different independent and symmetric populations, and we'll reject the null if it's the case that the difference of means is statistically significantly different from 0, either the case that it's larger or smaller. So now, what's our rejection region? Well, it's just the more extreme positive or negative values of the difference of sample means. And that's the best we can say until we can specify a critical value or a significance level for the test. So here's an example of what a one-tailed test might look like. We can test the null that the difference is equal to some value d naught, which is often just 0, against the alternative that the difference is smaller than d naught, as I've written, or that it's larger than d naught. Very often against the alternative that the difference is larger than 0. So in order to perform this test, we'll compute our test statistic. We're using the z statistic because by assumption we're working with large samples. Our standard error is one or the other from the previous slide according to whether we know the population variances or not. So the rejection region is just that the test statistic is smaller than our critical value corresponding to whatever is the significance level of alpha, or that our test statistic is larger depending on which direction of the one-sided test we're interested in. And remember, the one-sided test is going to put all of alpha into one tail. Well, here's the two-tailed test. It looks just the same, but with the analogous adaptation to the hypotheses, right? So here we're testing that the difference is equal to some d naught against the alternative that it's not equal to d naught. And it'll turn out that changing from the one-tailed test to the two-tailed test is not going to affect the test statistic. The test statistic is exactly the same. What does change is the rejection region, right? Because now we have half of alpha in each tail. All right, so here's an example for our most common test that there's no difference between population means. The null hypothesis is that there's no difference. The alternative is that there is a difference. And if we want to test at the 5% level of significance, then our rejection region is just going to be where the test statistic falls beyond 1.6 in absolute value, 1.96 in absolute value. This S bar here, there, that's just to abbreviate the standard error. And note I'm taking absolute values, meaning that we could reject for values to the left of negative 1.96 and to the right of positive 1.96. Alright, so here's a real example. Suppose we want to estimate the difference in means using the following sample data. So we have a sample of 121 with a mean of 3.27 and standard deviation of 1.3. And we have a sample of 125 with a mean of 2.53 and a standard deviation of 1.16. And we want a 95% confidence interval for the difference of means. Alright, well, here's our large sample confidence interval. We're going to use the sample standard deviations, or sample variances here, as the population variances are unknown. Well, essentially we're just going to plug in the values that we do have, and that lets us build our 95% confidence interval, which stretches from at the low end of 0.43 up to 1.05 at the high end. And we know that 95% of similarly constructed confidence intervals is going to contain the true difference of population means. Now notice here, this does not contain 0. So we can reject the null hypothesis that the difference is 0 at the 5% level. This is a two-sided test. All confidence intervals are just mimicking a two-tailed test rather than a one-tailed test. Well, let's formally conduct a hypothesis test using the sample data again, in case you're not convinced. So here it is as a reminder. Here's that sample data one more time. And here's the test. So we want to test the hypothesis of no difference against the alternative of a difference. So two-tailed test. And here's our test statistic using our really familiar formula by now. We'll find the test statistic is just z is equal to 4.71. Well, that's clearly bigger than 1.96, right? So we know there's evidence to support a difference in means. We're going to reject the null hypothesis of no difference in favor of the alternative hypothesis that there is a difference. Just like we would have previously by virtue of realizing that the confidence interval doesn't contain 0. And this is at the same significance level because we were going to have 2.5% in each tail. So you'll notice these two approaches give us the equivalent result, whether we're doing testing using the confidence interval or the two-tailed hypothesis test.